Swayam Prabha. Digital India. Educated India.
Okay, welcome everyone. So, today now what I will talk about is another type of optimization method, that is a full blown primal dual method. That means, it is a method that works in both primal and dual spaces, and moreover it gives no preference to either space. Okay, it works simultaneously in primal and dual spaces as if they are alike. As if they are of treats them on equal footing, and hence computes the primal and dual optimal solutions together simultaneously. This method is what is called an interior point method. Okay, so I will show you this interior point method only for the case of linear programming, because that is where it is easiest to explain, although this method has been extended now for nonlinear programming also. So, what is the idea? Suppose here is my linear program. I am minimizing C transpose x subject to Ax equal to b and x greater than equal to 0. And what is its dual? Let us write its dual in terms of a Lagrange multiplier lambda, or its dual variable lambda. So, its dual is this: maximize B transpose lambda subject to A transpose lambda. Now, the usual dual is that it is A transpose lambda less than equal to C, but instead of writing it this way, what I will do is I will insert a slack variable. So, I will write this as A transpose lambda plus S equals C and put S as greater than equal to 0. Now, what we have seen from our studies of complementary slackness and so on is that x and s are complementary variables. So, they would end up satisfying complementarity slackness or complementary slackness, which means, so x and s are complementary variables. So, they would end up satisfying complementary slackness, which means either x for each component, either xi is each component I, either xi is 0 or Si is 0 at the optimal solution, right. Now, one way of writing these optimality conditions is as follows. So, optimality conditions would be that A transpose lambda plus S equals C. I must also satisfy Ax equal to B. This ensures primal and dual feasibility. I must also have x comma s both greater than equal to 0. And I should have xi si, as I said, for every component either xi is 0 or si is 0. So, this is equal to 0, the product xi si is equal to 0 for all I from 1 to n, right. So, the difficulty in solving a linear program lies precisely in ensuring these two conditions. Out of these two conditions that have to hold simultaneously is what makes the problem difficult. The first two equations that one needs to solve are simply linear equations. So, those can be solved by using any classical technique. The trouble is we have to also satisfy x and s greater than equal to 0 and at the same and also the complementary slackness. Of these, even the complementary slackness condition we may say is eventually a nonlinear equation. So, it could be combined or clubbed along with these two as just as something of the same category as the first two equations, where the first two equations are simply linear equations. Well, this is an additional nonlinear equation, but then the trouble is also this particular inequality. This is now an inequality that needs to hold in addition to these linear stroke nonlinear equations, right. So, this is the challenge is ensuring that these two are satisfied, and that is what makes this complicated. So, the way to write, so the way we will, what we will do is, we will be trying to solve these as nonlinear equations, and at the same but our effort at solving the nonlinear equations would also ensure we will solve these as nonlinear equations while always ensuring that x and s are greater than equal to 0. So, effectively we are going to solve equation, the first, second and third equation as nonlinear, as a system of nonlinear equations, while ensuring that we do not violate equation 4, all right. Okay. So, that is the idea. So, now in order to express this, let us denote f x lambda s, denote this consider this function f x lambda s, and write this as, this function is going to be A transpose lambda plus s minus c, A x minus b, x s, and so this is x s and A transpose lambda plus s minus c, A x minus b, x s and 1, where 1, remember, is my vector of ones. It is a column vector of ones. Now, what is capital X and capital S? Capital X is simply a diagonal matrix comprising of the components of x, of the small x. So, it would, you can write this as diag of x, or equivalent of diag of x1 till xn, and S as diag of S1 till Sn. Okay. So, X is this matrix x1 till xn and zeros elsewhere, and S is this matrix S1 till Sn and zeros elsewhere. So, x times S is simply going, x times S is going to be another diagonal matrix. So, x S therefore, is another diagonal matrix where you have x1 S1 dot 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 till xn Sn and zeros elsewhere, and that times 1, the vector 1 is x S1 is simply going to give us this x S1 is simply summation of xi Si, I going from 1 till n. All right. Okay. So, this so what are we then looking for? We are looking for, we want to find, so in order to solve the optimization problem, we need to solve f of x this equal to 0 and x comma s greater than equal to 0. All right. Now, at the way we will do this is, we will do this iteratively. We will take steps at each at each iteration, and we will move in a certain direction at each iteration. The direction that we want to, but we remember, this is not just about solving nonlinear equations. This is, we also need to maintain feasibility with respect to x and s greater than equal to 0. So, this additional constraint means that it is not vanilla nonlinear equation solving. So, but we can take inspiration from the solution of nonlinear equations. So, we can write, say, we can take, say, for instance, a Newton step. Okay. So, we can take something like a Newton step. So, for instance, we can look for a direction for search as delta x, delta lambda, delta s, that satisfies this. Now, what have I written here? I have written j of x lambda s is simply the Jacobian of f. This is simply the j of x lambda comma s is simply the Jacobian. This is the Jacobian of f. All right. So, in short, what this equation is right. So, this is one can see that this is actually nothing but a Newton step. So, delta x, delta lambda, delta s is simply a Newton step for solving it. Now, if you so in a typical Newton iteration would do Newton iteration would do x k plus 1, lambda k plus 1 and s k plus 1 equal to x k lambda k s k plus the step that we have, right, which is delta x, delta s, delta lambda, delta. This would be the typical Newton iteration, that it would you start with your original the point where you are, compute the direction, and you add simply that direction to the point where you are to get your new iteration. But unfortunately, if you just simply, so what this would amount to is taking a full step along the Newton direction, right, Newton along the full taking a full step along the Newton direction, or along the Newton step. Now, that usually leads to a problem, which is that we need to remember maintain also feasibility with respect to the inequalities. So, if one takes a full step along this direction, so a full Newton step usually leads to x comma s greater than equal to 0 being violated. A full or typical Newton step, okay, would lead to this being violated. So, what we need to do therefore is to search along the Newton direction, all right, but search to the point where we do not violate this x comma s greater than equal to 0, right. So, the idea is to take inspiration from the Newton method, but do not go whole hog into the Newton method, because we are not really solving nonlinear equations in the most basic form, right. This is a much more specific and structured problem, and we are developing our own way of solving that particular problem for it. Okay. All right. So, now if you so what an interior point method point method usually does x k plus 1, lambda k plus 1, k plus 1 as approximately x k lambda k s k plus alpha times delta x delta lambda delta S. Okay, this is what it usually does. All right. Now, this now this also can be diluted further. So, what one even here, you do not want to go all the, so it's not merely that you do not want to, while it's not merely that you want to maintain feasibility with respect to this, and that is actually, this is one of the insights that led to this method becoming so successful, that one does not really want to, it is not just that you want to stay feasible with respect to this. If you did that, what you would end up doing is you would take a Newton step to the extent that you can without violating feasibility. So, you keep going along the Newton direction, and you will stop when you hit one of these quadrant lines, right. You would, when you hit one of these quadrant half spaces, you would stop. So, that would then take your iteration in this sort of manner. If these were your axes, say this is the x axis and this is the s axis, what it would do is it would take your iteration here, then here, then here, then here, then here, then here, and so on. Effectively, you would try to avoid, you would keep taking steps that would go all the way to the point where you will take as large a step as you can without violating the x greater than equal to 0 and s greater than equal to requirement. So, this is the x greater than equal to region, greater than equal to 0 region, this is the s greater than equal to region, right. So, you would say, starting from here, you would go up to the point where s becomes 0, x becomes 0, then from here you would go when x becomes 0, and so on and so forth. Now, an actual primal dual method usually does something even less aggressive. It doesn't go even this far. What it would try to do is, it would try to look at this kind of central region here, okay, and effectively it would make sure that your iterates remain within this central region. Okay. So, more concretely, the term that is often used is what is called a central path. Okay. A central path. A central path is simply is simply points, locus of points that satisfy x comma s, x times s equal to tau for some tau. Okay. So, and as you vary the tau, and as you make the tau smaller, you end up getting this central sort of path. Now, what we want your method to do is to follow this particular path that is given to it. Now, as a result, what it does is, the method does not sort of zigzag or go over from a point where one point where s is 0 to a point where x is 0, one of the x's is 0, and so on and so forth. So, effectively it actually does not ever hit any of the corner points of the polyhedra, either the primal or the dual polyhedron, and what it does, it actually reaches to the actual solution through the interior of the polyhedron. It gets to the eventual corner point solution, but through the interior of the polyhedron, right. So, that is the origin of also the name, the interior point method, right. If it did exactly any of these things, then it would be simply another way of doing what any of the older methods for linear programming were doing, which is simply searching over corner points of the polyhedron. Since we know the solution lies at a corner point, it would you would be simply going from one corner point to another looking for the solution. So, the interior point method actually abstains from doing that or refrains from doing that, and comes up and is therefore able to move directly to the solution. Okay. So, now So, the actual form or the diluted form is the following. So, in order to define it, let us define this particular thing, which is called the duality measure. Okay. So, duality measure is mu, defined as the 1 by n summation xi si. So, the duality measure is simply or equivalently written as x transpose s divided by. The duality measure is a measure of how far you are from satisfying complementary slackness. Complementary slackness would require the duality, if it is satisfied, the duality measure would be exactly 0, right. So, that is it sort of captures that particular property. Now, what your the actual new interior point method would do is that it would take a Newton step, but take it to the point where it towards a point where you are where xi si is close to some multiple sigma of mu. So, what we want to do is it does take a Newton step towards this particular path. So, in short, it is taking a Newton step, but trying to make sure that it remains in the vicinity of this central path, right, because xi, it wants all the products xi si to be around approximately sigma times the duality measure. The duality measure is an average of these xi si's. So, it is trying to make sure that all of them are within a multiple sigma, or roughly a multiple sigma of the average, all right. So, then the modified step is then becomes something like this. So, the Jacobian evaluates to A transpose I A 0 0 S 0 x, and then you have your step that you want delta x, delta lambda, delta s equals. Now, you have the right hand side, remember, was minus f, and minus f would be so this is now equal to minus r c, this is minus r b, and minus x s 1 plus sigma mu times 1. Okay. So, what is R c and R b? Well, R c is simply the residual, okay, the residual that remains from the dual constraint. So, the residual infeasibility of the dual constraint. R b is the residual infeasibility of the primal constraint. So, the actual what the actual method is basically doing is simply this. Okay. So, it's trying to find, it's taking steps in such a way that it satisfies this particular equation that has been written here. Okay, this is the master equation. So, let me write out the entire algorithm. So, the algorithm then is that initialize your x0 lambda 0 s0 such that all the components x0 and s0 are greater than 0. Okay. Now, for k equal to 0, 1, 2 dot dot dot, you solve the following. So, choose a sigma k in 0 to 1 and solve zero A transpose I A 0 0 S k 0 x k. Okay. Then you get a delta x k, delta lambda k, delta s k equals minus R c k minus R b k minus x k s k times 1 plus sigma k mu k times 1, where mu k is simply the duality measure at step k. It is equal to x k transpose s k divided by n. All right. You set x k plus 1 lambda k plus 1 s k plus 1 as x k lambda k s k plus alpha k times delta x k delta lambda k delta s k, where alpha k is chosen so that x k plus 1 comma s k plus 1 are greater than 0. So, already what it, so the way this algorithm has been specified, what it is already doing is it is sort of tilting your search direction in it more towards the central path, and you choose an alpha k, so that you can in such a manner that you do not violate feasibility. So, it is taking a step in along a modified Newton direction, tilted slightly more towards the central path, and asking you to proceed in that direction to the point where you do not violate the feasibility of the inequality constraints. All right. So, this is basically the idea. Now, there are much more concrete ways of making sure that you do not violate feasibility and you move towards the central path. For example, it is possible to define a neighborhood of the central path, and around that neighborhood and you keep searching till you reach that particular neighborhood. That is a more practical way of doing what the of implementing this sort of a method. Those are all details that can always be plugged in, but this is basically the overall, what I have explained is the overall structure of a primal dual method. So, what is the advantage of what is the result that we can expect from a primal dual method? So, a primal dual method is effectively what it does is, so what is it that one can expect from the primal dual method? What one gets a result that which essentially shows that your duality measure satisfies something like this, is less than equal to some gamma times mu k. where gamma, okay, where gamma is a constant that is between 0 and 1. So, the duality measure and the constant also depends, it might depend on n, but it is a constant between 0 and 1. So, the duality measure has this particular property that it goes down to 0 geometrically, right. So, mu k plus 1 is always less than equal to mu gamma times mu k, where gamma is some constant between 0 and 1. So, which means that for as k becomes larger and larger, your duality measure shrinks, and once your duality measure goes to 0, you would have satisfied complementary slackness. And the way you have designed your search is that it has always maintained feasibility with respect to this particular constraint. So, you have not only satisfied the linear equations, you have also made linear or nonlinear equations, you have also satisfied feasibility and then eventually satisfied complementary slackness, right. So, that effectively has ensured that so as k goes to becomes larger, you end up satisfying complementary slackness, and that effectively ensures that your method has converged to the solution, right. So, this is basically the essence of an interior point method. You can see the things that I mentioned to you at the start which is that it has made no distinction between the primal variable and the dual variable, right. It has searched simultaneously, or however you want to call it, it has computed simultaneously the primal and dual variables, and its effectiveness lies in being able to do this, in that it has computed both for you. It has attacked the problem jointly in the primal dual space, and in that space really optimization is not about a function over a set, but rather in the formulation that it is looking at. In that case, the optimization problem is a bunch of nonlinear equations that need to be solved, and that is what it has tried to do. Okay. So, with this I think I will stop with my coverage of the Newton method, and that also covers the algorithms that we plan to cover in this course. In the rest of this course, what I will now do is dynamic optimization and a little bit of dynamic programming to show you how exactly and relate that also to static optimization, the kind of optimization that we have studied so far.